Prim's algorithm. It's an alternative way of finding the minimum spanning tree of a network. Instead of working from a diagram, we're working from a table of values. Now, rather than go through each point in the algorithm, which is summarized here, I'm going to go straight to an example, and then I'll come back to this later. Here's an example of what a table of distances between nodes on a network might look like. These could be towns, for example. Before we go any further, look at the symmetry in the table. If I take any cell on the table, you'll see there that there's a mirror image running right down the middle of the table. All the values from any given cell are symmetrical. So if you're given a question where you have to work out some of the missing values, look for that symmetry and it will simplify your calculations. So here's how the algorithm works. We start with the node A. We place an arrow above the column and we say that A is now online. Now once A is online, we're going to rule a line through the row of values for A because we don't want A to connect back to itself. Now we look down the A column and find the shortest path, which will be the smallest number, and that's 300. 300 connects A to E, so we now say that E is online and we put an arrow above the E column. We also want to rule a line along the E row because we don't want to make unnecessary connections back to E. Now the rule is that you can only ever have one value on a row circled. You can have more than one value down a column, but you can only ever have one number circled on each row. Once we've circled the 300 on the E row, we can cancel out the rest of the values on the row. Now we look down both the A and D columns at the remaining values, and once again we're trying to find the smallest number, which happens to be 310 connecting A to C. So C is now online, and we put a line right through the C row to cancel that from further connections. Now we're going to look at all of the numbers remaining in columns A, C and E, and the next smallest one is 360, which brings G online. Place an arrow above the G column and rule a line through the G row. Now we look down all of the columns that are online for the next smallest value, and we find a 380, which brings F online, and we cancel out the F row. Once again looking for the smallest number, which is 210 connecting F to D, which means D is now online, and we cancel through the remaining values on the D row. Looking at all of the columns now except for B, and the smallest number is 330, F connecting B, so B is now online, and we put a line through B, and we're done. Now in this network there are 7 nodes, and just like working with the diagrams, the number of arcs we should have represented is the number of nodes minus 1. So we should have 6 values circled, which is in fact what we find. If we look at the diagram for the network, you could use Kruskal's algorithm here, and in fact I recommend you do that. Just take a couple of minutes to do it using that algorithm, and you should find that you get all of the same connections that we found from the table. So to sum up, let's make sure we understand the rules for how Prim's algorithm works. We're finding the shortest connection on an inline column, which is any column we've represented by placing an arrow at the top of the column. When we find the shortest connection, we circle it, and we automatically cancel all the other values in that row so that we don't make any unnecessary connections later on. That means ruling a line through that row. We keep going until all the nodes are online. If we have n nodes, we should have n minus 1 numbers circled. And the last point is very important. There may be more than one number chosen from a column, but no more than one from each row. And if you're careful to rule a line through each row as you go, you'll be sure not to make mistakes. Well, I hope you find that useful. As always, you should now do as many examples as you need to until you're completely confident.